Welcome back to Discovering Geometry with Mrs. Berry. This is lesson 36. This chapter is about circles, and today we will be talking about the properties of chords. Let's review some circle terms. We have concentric circles and congruent circles. Which one of these pictures is the congruent circles? Right here. These are the congruent circles. They have the same length radius. That means that their circles will be the same size. Over here, we have concentric circles. So the concentric circles are right here. Concentric means with center. They have the same center. So they're going to be circles inside of each other because they start from the same center but are different sizes. Radius, chord, diameter, and tangent. Which one is a radius? The blue one. This is our radius. It goes from the center to the outside of the circle. Which one is a chord? The green one. A chord goes from one side of the circle to another. It does not have to pass through the center. What about a diameter? The red one. A diameter goes from one side of the circle to the other and does pass through the center. It will be twice as long as the radius. And a tangent? This purple one. The tangent touches the circle at exactly 1 point. Major arc, minor arcs, and semicircles. So a major arc is going to be more than half the circle. This red one right here is going to be a major arc. The minor arc is going to be less than half the circle. So this red over here is a minor arc. And a semicircle is going to be exactly half. So this red one here, the red is a semicircle and the black is a semicircle. If this major arc is red, then the black will be a minor arc. Now we're going to look at examples and non-examples for the terms central angle and inscribed angle. So central angles are angles that, what? How can we change our definition? So we're going to write a definition for central angles based on these examples and non-examples. DOC, so this angle right here, so DOC intercepts the arc DC. Remember, the arc is part of the outside. AOB and BOC and DOA and DOB are all central angles of circle O. Over here on this picture, we have PQR, so this angle, and PQS and RST, QST, so QST, this angle down here, and QSR. All of these angles are not central angles. So what might our definition of central angles be? It looks like the vertex is at the center. So I might say that central angles are angles that have a vertex at the center of the circle. And their legs, or the rays of the angles, end at points on the circle. So does that make sense why all of these are central angles and these over here, none of them have a vertex at the center. So they are not central angles. How do we define inscribed angles? So in this first picture, ABC, BCD, so this one, and CDE are inscribed angles. Angle ABC is inscribed of angle, I'm sorry, ABC is inscribed in arc ABC, so the arc that goes all the way around, and it intercepts or determines arc AC. What about these angles? None of these are inscribed. So PQR, this one out here, is not an inscribed angle. STU, well, STU looks like a central angle, so that's not an inscribed angle. And VWX, this one over here, not an inscribed angle. What could we say about inscribed angles? It looks like their vertex is on the outside of the circle. This one was outside of the circle. This one was on the circle, but the leg didn't stay inside the circle. And this one had a vertex at the center, not on the side. So I think that we could say they're angles that have a vertex on the circle and they have to intersect an arc on the circle. And that's why VWX is not, it doesn't intercept an arc. All right, so inscribed angles have a vertex on the circle and they intersect an arc on the circle. Our second investigation, we're going to be looking at chords and their central angles. So you're going to need a compass, straight edge, and protractor. You're going to make a large circle with your compass, label the center O, and then construct two congruent chords on your circle. Label them A, B, and C, D, then make the radii that go from the center to each of the ends of the chords. With your protractor, measure BOA and COD and see how they compare. We're going to have a conjecture about that first. Then we're going to see, could you fold your circle to check your conjecture? The last step would be to evaluate the congruent chords. They determine two central angles that are congruent, and if two central angles are congruent, their intercepted arcs must be congruent. So that will be our second conjecture. Here's a picture of what you should have at the end. You have congruent chords right here. You're going to draw the radii. You're going to measure these inside angles, these central angles, and then we're going to think about how the arcs are related. So I drew my point in the circle. I drew my center because my point of my compass does not mark. And so if I draw my center first, then I know when I pick up my compass where that center was. I find it easier to move my paper rather than to move my compass because sometimes my compass will open or close a little bit. I'm going to label my center. Then I'm going to draw two congruent chords. So the way that I would do that is to draw a point on the circle and then switch your compass around and get a distance away from it. Then draw another point on your circle and do the same thing, get that same distance away. Then use a straight edge to connect those points to make two congruent chords. Now that you have those chords, you're going to be drawing in the radii from the end of each chord to the center O. There's my first central angle drawn. My second central angle drawn. Now I'm measuring that central angle. I end up using my ruler just to extend the ray so that I can get a good measurement on my protractor. And I can see that they're both 55 degrees in those central angles. How could I fold my paper to check? If you fold at the center, and mine was a little bit of a see-through, it wasn't quite patty paper, but I could see through it enough that I could line those up and I could see that those central angles were congruent. Because those central angles were congruent, I know that the arc measurements were both 55. So arc AB measured 55 degrees and arc CD measured 55 degrees. Our chord central angles conjecture. If two chords in a circle are congruent, then they determine two central angles that are also congruent. And what about the chord's arcs conjecture? If two chords in a circle are congruent, then their intercepted arcs are also congruent. Let's look at our third investigation. We're going to need a compass and a straight edge. You're going to construct a large circle, mark the center, and then make two non-parallel congruent chords. Construct the perpendiculars from the center to each chord. How does the perpendicular from the center of a circle to a chord divide that chord? With your compass, compare the distances from the center to the chords. Then you could try to see if the results were the same if you change the size of the circle or the lengths of the chords. So here we go, drawing a large circle. None of my compasses seem to hold quite straight, so I end up turning my paper to get a good circle. If you're having trouble with your compass, you could always use something very round, a can or a plate to trace to get a good circle as well. I was drawing my starting points for my chords. My chords are almost touching, but I'm going to go ahead and use them anyway. They're definitely not parallel. So here I'm marking my arcs to get my perpendicular. And my perpendicular bisector goes straight to the center of the circle. Now the last thing I'm going to do is compare the distances from the chord to the center along that perpendicular. Oh, I'm going to check. These are perpendicular bisectors. It divides that chord in half. So the perpendicular that goes through the center is the perpendicular bisector. And then I'm going to compare the distance along the perpendicular from the chord to the center. And it is the same on these congruent chords. A perpendicular from the center of a circle to a chord is the bisector of the chord. So it ends up being a perpendicular bisector. Divides the chord in half. Two congruent chords in a circle are equidistant from the center of the circle. Our last investigation is going to be about perpendicular bisectors of a chord. So we're going to construct a new circle. We're going to mark the center, and then we're going to make another set of two non-parallel chords that are not diameters. We're going to make the perpendicular bisector of each chord and extend them until they intersect. And then I think you'll be able to see, even from our last example, where that point of intersection is going to be. So here I've drawn two chords, and I'm going to make the perpendicular bisectors. Remember, I do that by making an arc across the top and the bottom of the line from either endpoint of the segment. And then when I connect where those intersect, I will get my perpendicular bisector. So I'm drawing my arcs on both of them, then using my straight edge to connect. And they both intersect at the center. And we saw that from our last investigation as well. When we drew the perpendicular to the center, it ended up being the bisector. So the perpendicular bisector would naturally go through the center of the circle. So our perpendicular bisector of a chord conjecture is that the perpendicular bisector of a chord passes through the center. It passes through the center of the circle. With the perpendicular bisector of a chord, you can find the center of a circle. Therefore, you could find the vertex of the central angle to any arc. So really, you need only to construct the perpendicular bisectors of non-parallel chords to help you with anything you're doing in the circle. We're going to look at an example that will be like your homework. AB is a chord. It's congruent to the chord CD. So then what do we know if these chords are congruent? Well, we are given that PO is 8 centimeters, and we're wanting to know what OQ is. Again, this is a perpendicular bisector. We would know that it divides it in half on both chords, but we also know that with congruent chords, they are equidistant from the center. So PO is the same distance as OQ. So OQ must also be 8 centimeters.